So now we're going to start, now that we've just done nothing but look at earth retaining systems and kind of sit back for one lesson, we're actually going to get started on our earth pressure theory. And we're going to get pretty detailed, I think, get to the fundamentals so we got some understanding where these numbers that we come from, that we use all the time come from. And we're going to start off by talking about what at-rest earth pressure is, because that's where we're going to start. So when we're done with this module, you definitely should be able to describe what at-rest earth conditions are, and also describe the boundary conditions that correspond to at-rest earth pressure. And then we're going to be talking about stress histories and how they affect at-rest earth pressure. So that's a key part of the discussion today. And I'm actually going to show you laboratory data to show you where some of the equations that I'm sure you're all familiar with, but where they actually come from. And the equation that we end up using all the time, which if you're not familiar with now, you're going to be familiar with very soon, certainly by the end of the lesson, is Mayne Kulhway's equation for K naught. And did I sign that as a reading for this? I don't remember. Probably not. Anyway, that's the basis. That's the equation we use for estimating K naught. And you definitely will know it, be able to recite it, and also be able to describe where it comes from and how it was created. So that's kind of our goals for today. All right. So let's talk about earth pressure limits and states of earth pressure. So we'll have a element, we have our element here under the ground at some depth Z. It's subject to a vertical effective stress and some horizontal effective stress sigma x. Now we know the vertical stress is easy to calculate, right? The total vertical stress is just the integral from 0 to z of gamma dz. We usually end up writing that as a summation of gamma sub I times h of I, because we usually pretend our soil is just like a layer cake and it's got different layers in it with different properties. So but that's really easy to do, and we know that from statics that has to be what's going on. You know, if you're a little guy standing down here holding this thing up, you've obviously got to hold up this entire column of soil above you. And all we're doing is taking the weight of the soil above you, dividing by the area, and that's the stress that's applied. So that we know. There can't be any concerns about that. Can't be any misunderstandings about what's going on there. And if it's a uniform soil, in this case, that's just going to be gamma z. Now and I wrote that as the total stress. The effective stress then is just going to be gamma z minus u. Now the horizontal effective stress then, we always define as K times the vertical effective stress, where K is the coefficient of lateral earth pressure. And we define it this way because there is no simple theoretical way to calculate the horizontal earth pressure, because it's going to depend on a lot of things. If we had some reverse fault near this location where this side was being upthrust against that, like that, we're going to get a very high horizontal stresses due to geologic conditions. The stress history is going to affect the horizontal stress. If the soil gets loaded and then unloaded, there's going to be some locked-in stresses. So there's not a simple boundary condition which we can use and calculate the horizontal stress. It's going to depend on a lot of different factors. And so instead of trying to look for a theoretical way to define the horizontal stress, we're going to use this factor. This is a simplifying thing that engineers do. Say, well, I don't really know what the horizontal stress is, but the vertical stress I can calculate any time. So I'm just going to call the horizontal stress some factor times the vertical stress, and let's see if we can figure out what that factor is. All right, and why is this not working? We define K as the ratio of the effective horizontal stress to the effective vertical stress. And that is, by definition, the lateral earth pressure, the coefficient of lateral earth pressure, or the lateral earth pressure coefficient. If there's no lateral strain occurring, then we have K0 conditions, which is what we call the at-rest earth pressure coefficient, or the lateral earth pressure coefficient at rest. So that's the theoretical description of K0. K0 is whatever lateral earth pressure you're going to get if there's no lateral strain. That still doesn't define it, because it still doesn't talk about whether there's loading conditions, non-loading conditions, and what the stress history is, but at least it's a theoretical place to start. So another way I like to think about that is, so if you drive out into site with your drill rig, before you get there and mess with the soil, right, before you do anything with it, you've got whatever God gave you when you showed up on site. That's K0. K0 is the lateral earth pressure coefficient before we went out there and screwed around with the soil, or did anything or built anything. We walk out on site, you're standing there, you look down, whatever stress is in the ground, we can calculate the vertical stress. If we could measure the horizontal stress, the ratio of those is going to be K0. So let's talk about the limits. So before we talk about what K0 is, let's talk about the limits that the lateral earth pressure could take on, because there's limits. You know, it can only get so high, it can only get so low. So that's the very first thing we're going to talk about. So to do that, we're going to do this magic trick. We're going to wish a wall in place. So we're going to magically not disturb the soil, but put this perfectly rigid wall in place. It's all magic. And once we've got it there, we're going to excavate. I'm going to excavate on the left-hand side of the wall as you're looking at it. And then I am going to push this wall to the right. So what's going to change as I push that wall to the right? Well, first of all, what's not going to change with my soil element there? Vertical stress cannot change, because it's just the summation of gamma z, right? So what is going to change? Which way is it going to go? It's definitely got to go up, right? And so if we could measure that as we push the wall, it would increase as the displacement. This is the horizontal displacement. Delta x is positive, means to the right, and we'll do a second, we'll do negative to the left. So as the displacement increases to the right, K, which is, remember, K is defined as the ratio of sigma prime x over sigma prime z. So K, because sigma prime z, this is constant, the denominator is not changing, so the numerator is going to increase. So the numerator is going to increase, so K is going to increase. But it's going to increase to a limit. At some point, at some displacement level here, it's not going to increase anymore. And this is just observation of behavior. We'll talk about why this happens in a minute. All right, so now we're going to go back to my wall that was wished in place. We're going to undo all that, go back to my wall that was wished in place. But now I'm going to let it move to the left. So again, the vertical stress is not changing. It's still gamma z. All right? This is always equal to gamma z. This is a boundary condition, really. This is equal to gamma times z, technically minus u. In this case, we're going to assume u is equal to 0. So what's going to happen to the horizontal stress in this case? It's got to decrease, and it means K is going to decrease. And that's exactly what's going to happen. K is going to decrease, and it's going to reach some asymptotic value, which we're going to call Ka for the active earth pressure coefficient. Now there's two important things in this figure that are drawn relatively to scale. One is the displacement at which you reach the passive displacement versus the displacement that you reach the active displacement. It takes very little movement to reach the active displacement, So very little movement on this side to reach the active condition. But it takes a significantly larger movement to reach the passive condition. And the other one is the relative changes from K naught to Ka and K naught to Kp. There's a much bigger change. In fact, it's even larger than drawn on this scale, but the change from K naught conditions to Kp conditions is much greater than the change of K naught conditions to K active conditions. And then what's the, if we order Ka, K naught, and Kp in order, which one's the lowest? Ka, and then comes the at rest, and then comes the passive pressure. So Ka is always less than K naught is always less than Kp. Now that's just observation. That just comes from observation. We can do this as a laboratory test. We could do field measurements, and we're going to see this kind of behavior. So defining what happens in this curve section is kind of hard, but let's see if we can figure out what these limits are. Okay, so I'm sorry. I'm getting ahead to the second lecture. Before we talk about what the limits are, let's talk about what we can say about K naught. That's what we're going to do for the rest of this module. Let's talk about K naught. Well, the first published information on K naught was done by Yaki. I'm not sure how you pronounce it. I'm not Hungarian. In 1944, he used a theoretical solution, and he came up with this equation for K naught from a theoretical analysis. For values of phi between 20 and 45, which covers, most soils under drain conditions, this is very nearly equal to 0.9 times 1 minus sine phi, which Yaki noted in his paper. In 1948, he simplified his equation to simply 1 minus sine phi, and it's in a separate paper published. By the way, this first paper was published in Hungarian and wasn't published in English until about 5 years ago. It wasn't translated into English about 5 years ago. There's probably hundreds of thousands of people that cite this paper as Yaki's paper demonstrating that the K naught was equal to 1 minus sine phi. And first of all, he never said it in that paper, and secondly, I doubt any of them have ever read that paper. So, I just read it a couple of years ago, so that's after it was translated into English. But this paper, which is from the First International Soil Mechanics Conference, I think, he published this 1 minus sine phi, which was in English, so everybody grabbed onto it. Now, this is a theoretical solution, and he purported this as a theoretical solution for the coefficient of lateral earth pressure at rest. And if you read some newer stuff, there's been a bunch of papers out, strangely by physicists, and I'm citing one of them here by Mikulovsky, that show that there's something wrong with his boundary condition as a theoretical solution, and it's probably not right. These are physicists. You got to like physicists. So, I guess the best thing to say is it's the theoretical basis of Yaki's 1 minus sine phi is questionable. You now know something that many people don't know. Because there are a lot of people that tell you, yeah, this is theoretically what K naught is. It's just really not that way in the field, but theoretically that's what K naught is. And that's not necessarily clear. And I've got the paper translated into English, and I'll post that for you. I don't know if it's on the blackboard right now, but I'll post it for you. And it's definitely interesting to read. And the 1948 one is there for sure. So let's talk about some other ways to get at K naught. Well, Skip Hendren in his PhD thesis in 1963 was looking at the behavior of sand under really high stresses. He was actually doing work for the Department of Defense related to the nuclear weapons business. And he did a theoretical solution. So if you had elastic uniform spheres And I don't know whether he used cubic close packing. He used a very, very uniform geometric spacing of them. So it's not, you know, at least a decent first order model of soils. He showed you have this really nice relationship between the horizontal stress and the vertical stress if there's no lateral strain. That's nice. So that's another place to start, and we'll come back to that one in just a second. Now, and then what he did was what is called K-naught strain path loading, or loading under K-naught conditions. So that's where you're going to load a sample where there is no lateral strain. So if you think about it, if we have an infinite deposit here, we have an infinite half space. So it goes infinitely far in this direction. Obviously, it goes infinitely far in this direction too, in what would be the y direction, which isn't shown in this figure. There can't be anything different happening in each one of these elements, right? If it's infinitely large in the same directions and it's uniform, isotropic, homogeneous material, they all have to be behaving the same. So, which means there can't be any strain in the x direction, because if there's strain here, then there would be something different going on over here. So there can't be any strain in this direction. We could also write that there can't be any strain in the y direction, although I'm doing this in 2 dimensions. Because if there's strain in the x direction, that means there's different displacements in one place and the other, and they can't be uniform. So that's we go back to that original definition of K-naught conditions. Is K-naught conditions is when there's no lateral strain. So if I do that, during deposition, what's happening to these soils is, we're just piling more and more soil on top of it. So sigma z is going up. Well, if there's no lateral strain, that means that these samples have to be undergoing uniaxial compression. In other words, they just have to be getting, as I load the soil up, let me change colors here. As I increase the vertical stress, these samples are going to get a little smaller, but they can't get any wider. There's just only going to be strain in the vertical direction. So it's uniaxial compression. And likewise, if I unload, then there's got to be uniaxial swelling. They've got to go up in this direction, but there can't be the only strain can be in the z direction. Can't be any strain in the x or y direction. Otherwise, it wouldn't be an infinite half space. So those are the boundary conditions for K-naught loading. And you'll see a lot of papers written on people talking about doing K-naught consolidation or K-naught load testing. So that's what they're talking about. They're doing testing where there's no lateral strain. So let's talk about, and these days we can do that right away in a triaxial cell with numerically controlled equipment. We can start loading the vertical direction, and we can measure the change in volume and have actuators control the cell pressure such that the soil consolidates without any horizontal stress. That's really cool. Well, you couldn't do that in 1960s, and so this is Hendren's test that he used to do that. And it's an odometer. It's a pretty big, hefty odometer because he was testing to very, very high stresses. So I have my soil sample in here. And it looks pretty complicated. There's some details here we're not going to talk about, but I'll point out the important details. And this is the actual loading system that he used. And then the soil is contained in a metal ring, just like you would in a regular consolidation test. It's a really thin, fairly thin metal ring, and he had strain gauges on it. And then behind the metal ring, and between the metal ring and the box of the apparatus, was an oil-filled space. And he had a null indicator system where they could increase this pressure in that oil. So the oil is not very compressible, so there's not a lot of strain. And they could increase the pressure in that annular space such that there's no lateral strain. So this is how he did K-naught loading. And he was doing this to really, really high loads. And they could also measure the lateral stress then, because he's measuring the strain he's measuring the pressure required to keep zero strain in the ring, and so he knows the lateral stress and the vertical stress. Does that make sense? You understand what's going on here now? It's a way to do under K-naught testing and measure the horizontal stress while you're applying a vertical stress. All right, so these are his results, or one piece of his results. So this is loading, so he's coming up this way and then down this way. So there's some, in the low stresses, there's a little something going on, but pretty soon he gets to a quite linear section. And we're going to use this notation, Konc, which stands for K naught for normally consolidated conditions. That's the notation he used. So this is K naught, right? It by definition it's K naught because there's no lateral strain. And NC means normally consolidated. What's a normally consolidated soil? That's a soil that's now at the highest stress it's ever seen. So during loading, the soil has to be normally consolidated. These are artificial specimens. He placed sand in these at different densities, and then started loading them. Okay, everybody with me? Questions? So that's K naught NC. And then on the unloading side, if you think about it, this is now an over-consolidated soil, right? This, if you want to think about it, is sigma prime C, the pre-consolidation stress. That's the highest stress it's ever seen. And now as we unload, the farther we unload, the greater the over-consolidation ratio is. Remember that the over-consolidation ratio is equal to sigma prime C divided by sigma prime 0, or sigma prime right now. So as you think about it, as I unload down here, at any point where I'm at, that's the current sigma prime, so that as I keep loading down here, as I go in this direction, OCR goes up. I'll give you a minute to look at that, make sure that sinks in. I guess I didn't point this out at the beginning. I'll make sure this is right. So this is the vertical stress, and this is the horizontal stress that he measured during the test. This is not a stress versus strain curve. This is horizontal stress versus vertical stress. Are we good? Because if you don't understand what's on the plot, then what I'm going to say next is not going to help at all. So he's applying a vertical stress, right? That's the independent variable. He measured the horizontal stress by measuring the oil pressure required to keep zero strain in the ring. And this is a plot of the horizontal stress versus the vertical stress. So the ratio of this, so K naught is rise over run. So that's sigma x over sigma z. In this case, the pore pressure is equal to 0, so that's their effective stresses. Okay? So unloading, we get a fairly constant one, and we unload. What happens to K naught? So K naught U means K naught in unloading. And I have K naught U1 there. That's K naught at this point right here, that area right there. So what happens as I keep unloading? What happens to K naught? Does it increase, does it decrease, or does it stay the same? K naught U, K naught for unloading. As I keep unloading, what's going to happen to K naught? It's just the slope of the curve. What happens to the slope as I unload? It increases, right? So at some other point here, at this point here, point 2, this is point 1. At point 2, this is my tangent, and that's K naught unloading at point 2. And what's the OCR at 2 compared to the OCR at 1? So I have OCR 1, OCR 2. What's the relationship between those? Which one of those is more over-consolidated? Yeah, because because the one on the left, the over-consolidation ratio is the current stress, the highest stress the soil has ever seen, divided by the current stress, right? That's the definition of the over-consolidation ratio. Right? So sigma prime C is not changing. The highest stress the soil has ever seen is not changing. And I'm decreasing the existing stress as I come down here. So OCR2 is greater than OCR1. And if I go to a third point, I come here to point 3. I got an even higher OCR, and I've got an even higher K. So as the OCR goes up, what happens to K? Sorry, this is going to be K not unloading. What happens to the at-rest earth pressure in unloading as K naught goes up? I'm sorry, as OCR goes up. It's going to increase also, right? So that goes up also. These are lab test data on, manufactured sands. I mean, this is lab test data on sands, reconstituted in the lab. All right, another thing that Hendren did is he did these tests at a bunch of different initial void ratios, in other words, denser and looser sands. So this is initial void ratio, and this is a plot of K naught, and this case, this is K naught ONC. So this is K naught for normally consolidated. So this is on the loading side. This is the normally consolidated K naught as a function of the void ratio. So where are the dense soils and where are the loose soils? Right, we got low void ratios on the left, so this is the loose side, and this is the dense side, right? Low void ratios on the left, high void. You got to remember void ratio. Remember, we geotechnical engineers were weird. We could have put density on that, but we like our void ratios. Right? Everybody with me? So the at-rest earth pressure decreases as the soil gets denser. Think about that for a minute. The at-rest earth pressure decreases as the soil gets denser. Which one of these soils is stronger, on the left or on the right? Did I write that backwards? Yeah. Sorry. I was right in my brain. Is that why everybody's looking at me weird? Should we try it again? This is high void ratio, so this is loose, and this is dense. Sorry. I don't know why my hand isn't working right. My brain was working just fine. So let's try that again. So we have dense on the left, low void ratios on the left, high void ratios on the right, dense on the left, loose on the right. So as the soil gets denser, K naught goes down. This is what I said, I think. Right? What about strength? Where's the soil stronger, on the left or the right? All right. So this is, and this is all for clean sands, so the strength is just phi, right? So this is for high phi prime, and this is for low phi prime. The implications for that will be apparent in a little while. And so, by the way, what was Yake's equation? I just wrote it here, but Yake's equation was K naught is equal to 1 minus sine phi. Does that work here? This phi goes up, sine phi goes up, and K naught goes down. Good. Everything's moving in the right direction. You like it when things move in the right direction. Next question is, are the values right? But at least we have the sign right. You like it when the positive is positive, and you think something's supposed to increase, and you measure it, at least it increases. And the question is, well, did it increase the right amount? So this is good. Yake says theoretically that as phi goes up, K should go down, and Hendren measured it. Woo! All right, so let's talk about it. So then he did actually look at, now he's looking at K naught, and again, this is K naught for normally consolidated. This is K naught during loading as a function of sine phi. All right, here's Yake's equation, 1 minus sine phi. Here's Hendren's equation for uniformly packed elastic spheres, and there are the data for 4 different soils. So we'll let it speak for itself. I mean, that's it. That's the data. I mean, that's all. I don't have much to say about it except that those are the data. So, good news. It's between. Hendren's solution can't be right because it's for uniformly packed spheres, but at least it gives you a bound on the answer. And boy, Yake's equation for one that may not be theoretically correct at least sort of goes through it. It doesn't look like it fits the data very well. If we ignore these for whatever reason and did a least squares fit, we're gonna. That's not a very good line. We're gonna get something more like this, right? But at least it's leaning the right direction and it's in the ballpark. That's pretty good for soils. All right. Now recall that, now we're going to talk about K naught and unloading, which is essentially K naught for over-consolidated situations. And so he noted that if you plotted K naught, and so this is K naught U, K naught for unloading, as a function of over-consolidation ratio, that you get this kind of hyperbolic function, that it increases but at a decreasing rate. And there was a fair amount of scatter in his data, but it fit in that band. So those tests are all on sands. And then Brooker, about the same time, a little later, but same era, did I'm not going to go through all of his tests, but these are tests on clay, in this case London clay, and I think he did several clays. In fact, I know he did several clays. But he saw the same behavior. This is in loading. So in loading, you seem to get a fairly, this is again axial stress on the independent variable, and he said in radial stress. He uses, I think, the same device, similar device anyway. So the slope of this is K naught, there's no lateral strain, and this is the unloading side. And he saw the same behavior is that that K naught increases as the over-consolidation ratio increases. Another way to think about that is you're just locking, when you load the sample, you're going to have some locked-in strain and some locked-in stress in a horizontal direction. I mean, anybody run a compaction test? Try to eject the sample after the compaction test? That you turn the mold over, it just falls out, right? You put it in a jack, and you jack and jack, and what's going on there? There's a really high horizontal stress. I mean, what's holding that sample in the cylinder? It's the friction. Why is it so hard to get out of the mold? Because there's a high horizontal stress. So there's a locked-in stress, and as you decrease the vertical stress more and more, the ratio of that locked-in. All right. So we have the same qualitative behavior with clays. What's the quantitative behavior like? Well, here's on the loading side. So for K naught for normally consolidated conditions, he tested 3 clays. He tested 3 clays and 1 silt. This Goose Lake flour is a silt, almost a pure silt. So here's Bear Paw Shale, here's London clay, here's Goose flour, here's Chicago clay, here's Wheeled clay. So 4 clays and one silt. Here's Yankey's 1 minus sine phi. Here's Yankey's 0.9 minus sine phi. Brooker went back and read the paper. And we'll talk about this line later, but this is the K active line. We'll talk about that one later. So these are actually doing a better job in terms of a linear fit. They seem to be lower than Yankey's equation by a little bit. This is under normally consolidated conditions, but the linear fit's better than it was with Sands. Remember, with Sands, it was pretty clear that it's pretty clear that the slope of the line, I probably should have drawn that in a different color. Let me do that. It was pretty clear that the slope of the line looks something more, if you did a best fit slope for the line, maybe that's not quite right, but it's going to be steeper than the line that Yankey had. But for the clays, the slope's better. The magnitude's not as good. I mean, best fit line through these is going to be someplace down here. So the slope's better, but the magnitude's off a little bit. So these are all tests on reconsolidated laboratory soils, which we did lots of in the 40s, 50s, 60s, and 70s, which is really nice, but as we know now, has something but not everything to do with real soils and really in the ground. Okay, so let's talk about some meta studies. So those are two of the earliest works. I like them because they show you they've got really good data. They show you qualitatively what's happening, but there's not a lot of data there. So let's look at some meta studies. So some of the early ones, Worth in 1973 tried to fit this equation to the relationship. We're talking about the relationship now between the K0 and the over-consolidation ratio. So he thought that the over-consolidated K was equal to the normally consolidated K times the OCR times the Poisson's ratio over 1 minus Poisson's ratio times the OCR minus 1. Well, it's not only a little complicated, but now we have to know Poisson's ratio. That's rather unhelpful for soils. Meyerhoff suggested this formula. Remember, as the OCR increased, we got decreasing. The rate of increase of the K was decreasing. So if you take the square root of K, that's good. It's going to be decreasing as the OCR goes up. So Meyerhoff fit that to a bunch of stuff in 1976. And then we have what has become the seminal paper on this and the one that we're all going to use. I'm sorry, was I going too fast there? Are we all caught up? We come to what's the seminal paper in this, which is Mayne Kulhway's 1982 paper. So they looked at a lot of data. They went out and got data on 170 different soils. These are still all laboratory tests. They got sands, they got clays. The notation that this notation not under normal consolidation. The first definition is like consolidated. And KOU which is by definition over-consolidated. All right, so these are their conclusions. For normally consolidated soils on the first loading, they compared K0 to Yankey's condition. So this is I've just written their axes bigger so you can read them. This is sine phi. This is Konc. So 1 to 1 is Yankey's equation, and there are the data. The solid data are for sands, cohesionless soils, and the open ones are for clays, for cohesive soils. their conclusions are Yake's equations valid for clays. Notice for clays, there's less scatter. I don't want to say there's no scatter, but there's less scatter, and they fit the line better. They say it's moderately valid for sands. For one thing, there's less range of friction angle in sands than there is in clays. So the fact that the curve is there's actually not that much difference in scatter about the line in the sands as there is in the clay. It's just that they're all clustered in the same area. Well, the friction angle of clays could vary from less than 10 degrees to 30-some degrees, where the friction angle of sands is only is much the range of values is much lower. So these are their these are Mayne and Kulhway's conclusions. Now, for over-consolidated soils, they noted that same hyperbolic function that we saw in Hendren's data of K0 during unloading versus OCR. So this same hyperbolic relationship. And Schmidt had suggested earlier using about the same time that some of those earlier papers came out, suggested using that K0 and unloading or the over-consolidated K0 would be equal to the normally consolidated K0 times OCR raised to some power. And if we go back to Meyerhoff's, that is Meyerhoff's equation, essentially that OCR is equal to the 1/2, right? That's what that says. So essentially, Meyerhoff he was using the same thing. He just said that the OCR was constant. The ratio alpha was constant. But it's obviously not constant. There's clear evidence that it should have something to do with the friction angle. Oops. So Mayne and Kulhway tried fitting it with a lot of things, and they found that if they use sine phi as the exponent, they really got a pretty good fit. Well, we'll show you the fit in a second. So I don't know what's going on here. So here's the fit with this is alpha. That's the hyperbolic parameter as a function of sine phi, and there are the data. So this is their good fit. There are some, and again, this is the same thing. We got cohesive soils are open, and cohesionless soils are closed. And there's clearly some things that don't fit it well. These are all peats, by the way. So we know peats have a very unusual structure. It's highly organic. So if we ignore the peats, that looks much better, right? And so the final equation that Mayne and Kulhway use is that K0 is equal to 1 minus sine phi OCR to the sine phi, which I suspect all of you have been using for some time. So what's important to say about it? Well, this is by far the most common way that we use to determine K0 today. It is completely empirical, right? It is completely empirical, and it's based on what? What kind of tests? Laboratory tests. Lots of laboratory tests, but it's all based on laboratory tests. There are some newer large-scale papers out that use larger samples with other fits to data, and I cite Hanna's. There's 2008, and he comes up with a different equation. From a practitioner standpoint, the answers aren't very much different than Mayne and Kulhway's, and it's already working okay, and we already got all the problems that really has nothing to do with what's going on in the field. So the difference between the uncertainty between some of these theoretically better solutions and Mayne Kulhway's is way overshadowed by our uncertainty of taking these fits to laboratory data to the field. So Mayne Kulhway is probably as good as anything. But now you know from whence it cometh. And that is a good time. First, if there's any questions.